Logarithms often feel intimidating, but they're really just another way to express exponents. Think of them as secret codes for exponents. Let's break it down together. In the simplest terms, a logarithm answers the question, what power do I need to raise a base to in order to get a specific number? For example, let's say we want to find the logarithm of 100 with a base of 10. What this really means is, what power do we need to raise 10 to in order to get 100? The answer is 2, because 10 raised to the power of 2 or 10 times 10 equals 100. We write this mathematically as log base 10 of 100 equals 2. Here, 10 is the base, 2 is the logarithm, the power, and 100 is the result. It's like a little mathematical puzzle where the logarithm is the missing piece. Don't worry if it still feels a little fuzzy, we'll dive deeper into more examples and explanations in the following sections. By the end of this guide, you'll be a logarithm pro. Remember, logarithms are just a different way of looking at exponents, and with a little practice, they'll become second nature. Let's explore them further. Before we can truly understand logarithms, we need to make sure we're comfortable with exponents because they're like the building blocks of logarithms. Remember, an exponent tells us how many times to multiply a base number by itself. For instance, 2 cubed means we multiply 2 by itself 3 times, 2 times 2 times 2, which equals 8. Here, 2 is the base and 3 is the exponent. Pretty straightforward, right? Exponents can be any real number, including fractions and decimals. But for now, let's focus on whole numbers. One important thing to remember is that any number raised to the power of 0 always equals 1. For example, 5 to the power of 0 equals 1 and 100 to the power of 0 equals 1. Another key concept is that exponents only affect the base they're directly attached to. For example, in the expression 2 times 3 squared, only the 3 is being squared, not the 2. So the answer would be 2 times 9 equals 18. Now that we've refreshed our memory on exponents, let's move on to how they relate to logarithms. Remember how subtraction is the opposite of addition, and division is the opposite of multiplication? Well, logarithms are the opposite of exponentiation. They undo each other, just like those other inverse operations. Think about it this way. If we raise a base to a certain power, the logarithm with that same base tells us what that power was. For example, we know that 2 cubed equals 8. The logarithm with a base of 2 that gives us 8 is 3, written as log base 2 of 8 equals 3. This inverse relationship between logarithms and exponents is key to understanding how they work. If you know the exponent, you can find the result of the exponentiation. Conversely, if you know the result in the base, you can use a logarithm to find the exponent. This inverse relationship is super helpful when we're trying to solve equations that involve exponents or logarithms. We can use logarithms to get rid of exponents, and we can use exponents to get rid of logarithms. More on that later. Let's first explore logarithmic functions a little further. Now that we understand the relationship between logarithms and exponents, let's dive into logarithmic functions. A logarithmic function is simply a function that involves a logarithm. It's usually written in the form f of x equals log base b of x, where b is the base of the logarithm. Just like exponential functions, logarithmic functions have some important properties. One key property is that the logarithm of 1 is always 0, regardless of the base. This is because any number raised to the power of 0 equals 1. For example, log base 10 of 1 equals 0 because 10 to the power of 0 equals 1. Another important thing to remember is that logarithmic functions are only defined for positive values of x. This means we can't take the logarithm of a negative number or 0. Now let's talk about two special types of logarithms: common logarithms and natural logarithms. Section 5. Common logarithms and natural logarithms. In the world of logarithms, there are two superstars that we use all the time: common logarithms and natural logarithms. Common logarithms use a base of 10, so when you see log written without a base, it's implied that the base is 10. For example, log of 1000 means log base 10 of 1000, which equals 3 because 10 to the power of 3 equals 1000. Natural logarithms use a special number called Euler's number, represented by the letter E. Euler's number is approximately 2.71828, and it pops up in all sorts of cool mathematical and scientific contexts, especially those involving growth and decay. Natural logarithms are written as ln of x instead of log base e of x. So when you see ln, just think natural logarithm with a base of e. Both common and natural logarithms are super useful in different areas of math, science, and engineering. Now that we've met them, let's see how we can use logarithms in equations. Section 6. Using logarithms in equations. One of the most powerful things about logarithms is their ability to help us solve equations that would otherwise be tricky or impossible to solve. Since logarithms are the inverse of exponents, we can use them strategically to isolate variables and find solutions. For instance, let's say we have the equation 2 to the power of x equals 16, and we want to solve for x. We can use a logarithm with a base of 2 on both sides of the equation to get rid of that pesky exponent. Log base 2 of 2 to the power of x equals log base 2 of 16. Since the logarithm and the base on the left side cancel each other out, remember, they're inverses, we're left with x equals log base 2 of 16. Now we just need to figure out what power we need to raise 2 in order to get 16. Well, 2 to the power of 4 equals 16, so log base 2 of 16 equals 4. Therefore, x equals 4. We've successfully used a logarithm to solve for the exponent. Pretty neat, right? Similarly, we can use exponents to get rid of logarithms in an equation. The key is to use the inverse relationship strategically to simplify the equation and solve for the unknown variable. Now that we know how to use logarithms in equations, let's practice calculating them. Section 7. Calculating logarithms. Calculating logarithms might seem daunting at first, but it's actually pretty straightforward once you get the hang of it. We can use our knowledge of exponents and the inverse relationship between logarithms and exponents to figure out the value of a logarithm. Let's start with a simple example. Log base 2 of 8. This asks, what power do we need to raise 2 in order to get 8? Since we know that 2 to the power of 3 equals 8, the answer is 3. Therefore, log base 2 of 8 equals 3. Sometimes the calculation might not be as obvious. For example, what about log base 5 of 125? We need to find the power to which we raise 5 to get 125. A little trial and error might lead us to 5 to the power of 3 equals 125. So, log base 5 of 125 equals 3. In some cases, we might need to use a calculator to find the value of a logarithm. Most scientific calculators have buttons for common logarithms, log, and natural logarithms, ln. Just enter the number you want to find the logarithm of and press the appropriate button. Now that we know how to calculate logarithms, let's explore some real-world applications. Section 8. Real-world applications. Logarithms might seem like they only exist in the realm of math textbooks, but they actually have a ton of practical applications in the real world. For example, in chemistry, the pH scale, which measures the acidity or alkalinity of a solution, is based on logarithms. A change of 1 unit on the pH scale represents a 10-fold change in acidity or alkalinity. Logarithms are also used in finance to calculate compound interest and loan amortization. They're essential in fields like computer science for algorithms and data analysis. In music, logarithms help us understand musical intervals and scales. The Richter scale, which measures the magnitude of earthquakes, also uses logarithms. Each whole number increase on the Richter scale represents a 10-fold increase in the amplitude of seismic waves, which translates to a significantly more powerful earthquake. These are just a few examples of how logarithms are used in various fields. They're powerful tools that help us make sense of the world around us. Section 9. Tips for mastering logarithms. Mastering logarithms, like any mathematical concept, takes practice and a little bit of patience. Here are some tips to make your logarithm journey smoother. Remember that logarithms and exponents are best friends, and they undo each other. This inverse relationship is key to understanding and working with logarithms. The more you practice calculating logarithms and solving equations involving logarithms, the more comfortable you'll become. Start with simple examples and gradually work your way up to more complex ones. If you're struggling with logarithms, don't hesitate to ask your teacher, a tutor, or a math-savvy friend for help. Sometimes all it takes is a different explanation or approach to make things click. Logarithms might seem a little mysterious at first, but with a little effort and the right attitude, you can conquer them. Remember, math is all about patterns and relationships. And once you see how logarithms fit into the bigger picture, they become much less intimidating. So, go forth, embrace the power of logarithms, and watch your mathematical confidence soar.